YouTube. No, they'll give you a link.
Oh yeah, more fun coming.
Yeah, it's going live. Yeah.
The share buttons.
Yeah. Send me this link. I'll have to tweet with this link. I'll have to email all of them.
Yeah.
Keita was there. Sanjay, Alessandra, and Anitha counts. Let's say hello.
Sure.
So all the best. I'll come back and see if they're still around.
Yeah. So where did you send it?
On Slack.
Yeah, but then there are two links here because there's also Google Drive link. I don't want to actually. Okay, what do you? Otherwise, I can go to YouTube now, change the thumbnail. Right? But it's okay.
It's okay.
29. It's already 29. So this is ready. This is ready. This is ready. I have to email people for whom I send emails, which is not great. Yeah. So let's just.
Or in that YouTube, the previous link, the stream, in the description, we can put a new.
Yeah.
One.
That also. Let me just check. What did I send? Yeah, Anitha is saying something.
So let me know if any other things are required.
Yeah, I am.
So, yeah.
This is good. Okay, link पे जाना. तो they can join Google Meet. Okay, what else? कल करके भी हो गया. So let's change the link. So now I can go to my. Now I can go to my stream. That's live, right?
Yes, it is live.
Yeah. So I think Anthony is saying something. Technically, I'm there, but oh, okay. So I have to join to meet for sure because I'm the one who can let people in. Alessandra, all of them are online. Yeah. That's okay. Okay, Anupman and so can you keep a watch on people watching this also? You can see the chat here. Oh, you won't see the chat here. Okay, drop chat. Okay. I'll post the slides also. No, just I said. Anvitham and Alessandra, Sanjay. Sanjay, you can hear us. Sanjay, can all the at least the examiners speak? Anvithaman, can you just speak so I know it's. Anvithaman, I can't hear you. You're on mute. Sanjay, can you just speak, Sanjay? Yeah. Thanks, Sanjay, for joining. Yes, Anvithaman, I can hear you. Thanks. Yeah.
So, I've been saying that for a long time.
So we are also live streaming it on YouTube. So let's see how that goes. No, I don't think so. You're going to speak now. So when he speaks, when he's done with speaking, when we speak internally, we will not do YouTube Live. Don't worry. Only his talk, we're trying to make more people access to the content. That's all. So live stream is not the Google Meet feed. Meet feed is not being live streamed. Only this part is getting live fed into YouTube. Okay, let's get started. Thanks, Sanjay, Alessandra, and Luthman for joining, who are the examiners. Thanks others also who are joining on Google Meet, which is the internal platform that we're using. Thanks to people on YouTube, which is our external platform, which is people outside IIIT Delhi for them to access this content very easily. Thanks everyone for joining. So it's Rishab's PhD thesis defense, and the way we'll do it is he will take about 45-50 minutes to present his defense. Then we'll have students, others ask questions. During this 45-50 minutes, only for clarifications, which is if you don't understand anything in the slide, unless you will not understand anything in later, you think you'll not understand anything in later, without knowing that slide, please ask. So he gets 15 minutes fully for himself. Then students, examiners, live questions if you want to ask during that time, so that others who are in the, so to say, students who have joined the call may benefit from this. There are many PhD students who have joined the call, so they will benefit from the kind of questions that you're asking. This is after he's done. At that point in time, we'll also shut the YouTube live. And then the students all leave. All students leave. Only the examiners and Rishab and myself will be in the call. That will be only the meet call. And that's more like drilling, more exhaustive questions, all that. And then Rishab also leaves. And then we'll make some judgments about the defense. Is that okay? For people on mute, just a small request, please mute yourself. If you have any questions, please type it in the chat. I will monitor the chat so I can actually ask Rishab the question. Is that okay? Rishab, okay.
Okay, thank you, PK. Hello, everyone. I am Rishab Kaushal, PhD student at IIIT Delhi, presenting my PhD defense presentation on the topic of user identity linkage, data collection, dataset biases, method control and application. At the outset, I sincerely thank my evaluation committee members, Dr. Sanjay, Dr. Alessandra, Dr. Anvita Aman, and Dr. PK, who is my PhD advisor. I am a sponsored PhD student at Precog Research Group. We are a group of researchers who investigate security and privacy problems on online social media. I also serve as assistant professor in IT department at Indira Gandhi Delhi Technical University. I have done my masters from IIIT Hyderabad, and social computing is my research interest. So here is going to be the outline of my talk. I will start with the background, problem statement and motivation, and then move on to the other parts of my PhD thesis. Identity. So there is a grand philosophical question of who am I? And there are many philosophies, theories, ideas who have tried to propose a solution to this grand question. And most of these inquiries and methods have investigated in the inner world. But from the outside world, each person is identified on the basis of the roles that he or she plays in the society. So the same person may be a student, teacher, father at the same time as perceived by people in the society. So just as the same person has multiple identities based on the roles that the person is playing in the society, in the same way, the same person in the online world has its presence or identities on multiple online social networks. So for instance, there are many motivations to do that. There are a lot of professional networks like ResearchGate, LinkedIn. There is a personal network like Facebook and Instagram. And then there are networks like Twitter where you can get access to real-time news. And the same person joins these multiple social networks, creates his identities, or in other words, accounts. So the word accounts and identities we will be using them interchangeably. And this identity has three dimensions: the profile, content, and network. The profile settings that the person does, the content that the person shares, and the friends that the person keeps. So in this scenario of user joining multiple social network, it brings us to this interesting research problem, which we refer as user identity linkage. So user identity linkage refers to the problem of determining whether two input user identities taken from two different networks, A and B, whether they belong to the same person or not. So here the goal is essentially to learn a function f, which when given two user identities, IA and IB, if the two identities belong to the same person, that function should return 1, otherwise it should return 0. And we refer to identities IA and IB as linked user identity pair. So there are many motivations to solve this user identity linkage problem. The first is a use case of cross-platform recommendation. So let's say there is a user who is very active on Twitter and makes a lot of tweets, and then this user suddenly decides to have any data on Facebook as such. But if we know that this user is actually the same user from Twitter, then we can target advertisement to this user. In the same way, in another scenario, let's say there is a celebrity and the celebrity is a star, and the star celebrities tend to have large number of following, and we tend to create social capital out of these followings. A naive method would be to simply add the following, but there would be a number of common followers, So a better approach would be to find out the common people who are the common followers and remove these out while calculating the true social capital. Then the other motivation is the background checks. So let's say there is a candidate and candidate applies to an organization. So the candidate submits his resume to the HR manager, and in the resume the GitHub and LinkedIn details are mentioned. Now the HR manager, in order to perform a background check if the identity of this user on these multiple platforms, if this can be linked to the same user identities on other platforms like Facebook, Instagram, Twitter, and Stack Overflow, then a more behavioral characteristic profiling of the user can be. Then another scenario, let's talk in terms of the advertiser. Advertiser needs to send advertisements to a bunch of people on both Facebook and Twitter. But there could be few common users. So this user on Facebook is the same as this user on Twitter. So therefore, in order to reduce the advertisement budget, if we have already targeted this user in Facebook, then we need not target the same person on Twitter. So although all these motivations may tend to look from the point of view of user identity linkage problem, but later in this talk, we will also talk about a project where we also looked at how the user can be safeguarded from these linkages. So with the motivation and the problem statement, it brings us to the core thesis question, which is computational approaches can be proposed for the analysis of data collection method, which is part 1. Investigation of biases in identity linkage datasets, linkage of user identities across social networks, controllability of user identity linkage, and application of user identity linkage to solve extraneous problems. So with that, we move to the first contribution of our PhD thesis. So I look at the data collection aspect. So the goal of data collection methods in the context of user identity linkage is to find the linked user identities. So let's say there are two social networks, A and B, and there are identities, and one that is given in red circle in A and the red circle in B are identities belonging to the same person. So the goal of a data collection method N would be to capture such linked user identities. And there could be some user identities which could not be linked by a data collection method. So here is the first method, which we refer as social aggregation. And there are a number of platforms on which users create accounts and provide details of their multiple social network accounts. For example, about.me, Linktree, bio.fm. So there are many motivations for users to do this. For instance, in about.me, the reason would be that the person would want to have more visibility of his identities. And in case of bio.fm, the motivation would be that there would be a single interface on which the user is able to see all his identities. So, irrespective of the motivations, there are such websites, and in our PhD thesis, we looked at the about.me pages and we extracted the linked identities which were specified by the users themselves on the about.me. Then the other method is referred as cross-platform sharing, which refers to the user behavior in which user posts the same content across multiple social networks. So for instance, in this diagram, you see on the left is a Twitter tweet, and there is a link to the Instagram post. In fact, what it means is that this post was originally posted on Instagram and then it was shared on Twitter. And when it appears on Twitter, it appears in the form of the Instagram URL. So we looked at such tweets which had the Instagram URL, and another additional check was done to ensure that the source of this tweet is coming from Instagram to collect such link identities of the same user. Then the third method we looked at is the self-disclosure. So this is an example of a Twitter profile setting page where there is one URL, and in this URL the Twitter user can put any URL of either his homepage or his identity to some other social network. So we looked at the profile settings of Twitter user, and whoever has mentioned some link to another social network, so we collected linked user identities for the same user in this way. So coming to what we found, so we found a large number of social networks, and on the y-axis are the number of user identities. There are few social networks on which we found large number of user identities, more than 10,000 user identities, and there were also a large number of social networks where the number of identities were not as large as they were earlier. Then this is a graph which shows how many identities does every user have in the data that we collected. So for instance, number of users who have 2 identities are close to 100,000, and then number of identities with number of identities which are 3, 4, or 5 are close to 10,000. And as we go to the right, as the number of social identities per user increases, the number of such users will be decreasing. And here is a snapshot of the top 6 social networks where we got the best coverage are plotted. So for instance, Twitter and Instagram, with this pair, we were able to get 62K linked identity pair. For Facebook, Twitter, we got 49K. For Google Plus, Facebook, we got 12K, and so on. So one thing to observe across all of these social network data collection methods is one thing, which is that most of these behaviors depend upon a particular user behavior. For example, cross-platform sharing method depends on the fact that user cross-posts. Or self-disclosure method depends on the fact that user himself mentions the identity of another social network on the homepage link in this profile settings. So, having developed the computational approaches to collect user-linked identity pairs, and having known that they depend on users, we investigated in the second part of the thesis on the biases that get manifested because of these user behaviors. So every data collection approach depends on a typical behavior, as I said earlier, and as a consequence, these behavioral biases exhibited by these users get manifested. So we focus on 2 data collection methods, which is self-disclosure and cross-platform sharing. And we focused on 2 social networks, Twitter and Instagram. And the aim was to do detection of bias, measure the impact of bias, or quantify the amount of biases that were there in the linked identity datasets. So this is a typical supervised learning framework where in the first part we showed that there are 2 social networks which are the source of data. We use 2 different data collection methods to collect ground truth positive identities, which are the identities that belong to the same person. And then, in order for the machine learning classifier to work, we also needed a negative class. So we did a negative class generation to create unlinked user identity pairs, which is the user identities that do not belong to the same person. And this was done in 2 ways. The first was done as similar pairing and the other was done as random pairing. So let me quickly explain this. So if the positive pair that we obtain from any one of these methods, let's say is Rishab K underscore comma RK dot triple IT, then from the negative pairing, in case of the negative pairing, the first option is that we do a similar negative pairing, by way of which I mean that I look on Twitter and I look for similar usernames. So Rishab without the H, A underscore the similar username. So I get it with RK.IT, and this is one negative pair which we call as a similar negative pair. And the other is a random negative pair. Rahul was some username obtained in one of the positive pairs, so we paired that user with the pair that we obtained. So this way we created two types of negative linked identities or unlinked identity pairs rather. And then for the feature engineering, we looked at the attributes, mainly the username and the display name of user identity that we have received, and we computed different similarity metrics. So we computed Jakarta similarity and edit distance.
So Rishab, there's a comment. So just try and explain this. So Anjali is saying at this point it may be best to define more precisely what is meant by bias, since the term itself can mean so many different things. To understand well what precisely is being directed, just say what's the definition of bias.
Yes. In this basically what our whole aim of detecting the biases or how do we define biases is something which is coming in these couple of slides. So let's say, for example, the bias effect that we saw was in terms of the features, in terms of these features that were obtained at this stage. And if you look at the distribution of these features, this is a Jakarta similarity on usernames. And it turns out that most of the linked user identity pairs obtained from self-disclosure had a higher similarity on usernames. So almost 50% as opposed to only 23% from the CPS. So the feature Jakarta similarity distribution for one data collection method was observed to be much different than the other distribution. So it means that for some reason the users who are doing self-disclosure, they keep their usernames more similar than the users who are doing cross-platform sharing. And the similar trend was observed with another metric, edit distance. So smaller is the distance, greater is the similarity on display names of the linked identity pairs, and we observed that in self-disclosure, a large set of linked identity pairs showed more similarity in the display. Then we also looked at what is the impact of these observed biases on different machine learning models. So we performed two kinds of experiment. One was with the same data set, the other was with different data set. And the dark blue and the dark orange bars here represent that the same data set was used for train and test, and the light blue and the light orange correspondingly represents those experiments where different data set was used for training and different was used for testing. So we observe that the performance is decreasing across all the machine learning models as measured on precision. So having observed these biases and observed their impact on the machine learning algorithms, we now look at how we can quantify these biases. So for this, we made use of situational testing which is typically used in discrimination studies. So here is the background. Let's say you have a data set, and the data set has many attributes and many data instances. One of the attribute is referred as the protected attribute, and there is a class attribute. So class can be selected or not selected. Protected attribute could be, say, gender, and the gender has two values, male and female. So the protected group comprises of all those data instances where the value of protected attribute is female, and similarly we have the unprotected group where all the data instances are those where the gender is male. So given this background, the quantification metric goes like this. Given a data instance, in this case, let's say female, and then there is a class label, and we find k nearest records. So the nearest records are found by looking at the attributes which are not including the protected attribute and the class label. We find the k nearest records in both the protected group and unprotected group. So let's say k is 4. So for a given record, we find k nearest neighbors for this record and k nearest neighbors in the unprotected group. And we find that 3 out of them are belonging to the same class in one group, which is the protected group, and in the unprotected group, only one belongs to the same class. So there are two metrics to quantify this phenomena, which is P1 and P2. So P1 is 3 by 4, P2 is 1 by 4, and then we define the T value. So it is the T value which is the quantification metric. So if the T is 0, which means the proportion of users on both these groups are same, then we actually say that there is no bias. Otherwise, we say that this particular data instance is suffering from a discrimination. So how did we apply? We applied this situational testing framework to quantify biases. In the context of our problem, a data record refers to, which was referring to a person, is now referring to a identity pair, and the protected attribute, which was gender, is now data collection method, which is SD or CPS, and the class label was selected or unselected. We map it to linked or unlinked user identity. And this is one of the results. So we investigated whether both the classes, linked and unlinked, data instances were equally affected by the bias. It turns out that P value is 0 if there is no bias, but P value 0, there were only few records concentrated at the center. But then there were a number of records on both sides, positive and negative, which were affected by the biases. So basically this work proves the fact that there are biases inherent in the data that we collect, and we can quantify these biases. And we recommend that future studies on identity linkage should use more than one data collection method. But mitigation of biases is something that is an open question. So with this, we move to the next part, which is the method contribution of my thesis. In this, we contribute at the level of method. So we try to solve the identity linkage problem at the level of method by proposing next link framework. So in the next link framework, our aim is to obtain effective node representations such that the node representations or the node embeddings of users that belong to cross-network linkages, so this is essentially the linked identity pairs, are closer in the embedding space than the other. So let's say there is two social networks, one with nodes blue, one with nodes green, and there are the cross-network linkages. So the goal is to convert these nodes into an embedding space where the cross-network linkages, the nodes that belong to the C and Ls, they come closer in the embedding space. And more formally, it can be defined as a function which learns from the given user identities and converts them into their embedding low-dimensional vectors, such that the similarity between Zi and Zj in social network X and Y respectively is very less, or rather they are more similar. The distance is less, they are more similar, as opposed to other pairs which do not belong to the same user. So we did learn these embeddings in two ways. The first phase was to learn the local node embeddings, and in the local node embeddings, the goal is to preserve the structural similarity of nodes within the same network. And in the global node embeddings, the goal is to preserve the similarity of nodes across the two networks. And there are different formulations and different ways in which these embeddings can be learned. So it turns out that concatenation gives us the best result. So we concatenate it. The embeddings obtained from local node embeddings and global node embeddings, created a common embedding vector, measured the similarity using cosine similarity. So the local node embedding, so given that next link is a framework, so the local node embeddings were learned by using a well-established line algorithm. So line algorithm has a couple of steps, which is there is a joining probability, which is measured in terms of a softmax kind of a formulation of these embedding vectors. So our goal is to learn these vectors. And then there is an empirical probability which is coming from the network itself. So the network itself is giving us what is the probability that this node and this node are connected with each other. So it is proportional, it is equal to the weight and sum of weights of all the edges in the graph. So, so this is the observed probability distribution. This is where we want to learn these embedding distributions. And one of the formulations is to use KL divergence between the two probability distributions as the optimization objective function. Then in terms of the global node embeddings, we constructed a global network, a global graph. Global graph G is constructed. All the vertices of graph X and Y are taken together, and cross-network linkages and non-cross network linkages. So cross-network linkages are the linkages between link identity pairs, which is in this diagram is depicted in solid edge, and the non-cross network linkages is represented by the dotted edge. And this dotted edge is what we refer as a negative edge generation. So how do we generate this? Is we perform a random walk starting from this node, and we do this random walk here, and let's say we reach to this node, and we know that this node is on the random walk. So we create this negative edge from this particular node that we found on the random walk to the corresponding node of this linked pair. So after generating this global graph, the idea was to learn node embeddings, and to learn node embeddings, we made use of the biased walk of node to web. However, we guided these biased walks by the common friendship metric. So common friendship metric is again based on a very common notion that two nodes are going to belong to the same person if they have more common friends. So this is the transition probability during this walk, and this probability is proportional to the common friendship metric. We evaluated this approach on two data sets. Augmented data set was obtained by sampling a single large Facebook friendship network comprising of 63K nodes and 817,000 edges. And another data set was a real world data set which is comprising of Twitter and Instagram. So creating two sub-samples from a given graph has already been tried. So such kind of synthetic data sets have been created, and this data set is kind of a de facto data set. A number of prior works have used this data set. So we wanted to use a standard data set to evaluate our method. And the evaluation was like this. So let's say you have a user UI in network X. So the goal is to find uj y, which belongs to the same person. So therefore, the zj, which is the embedding corresponding to this node uj in the social network y, is what we want to find. And we obtain the top k node embeddings, ordering them based on the cosine similarity. If z of j is present in these top k node embeddings, we say a hit has occurred, and we do a summation of all such hits for all the cross-network linkages. So we compare our approach with two other state-of-the-art approaches which are solving the same problem of user identity linkage, which is IONT and legal. And it turns out, except for the value k equal to 1 or 2, maybe for all other values of k, the hit rate at the rate k for our proposed next-day framework, which is a combination of line and node to vec, performs better. So this essentially concludes this work of learning node embeddings.
Sure. Anvithuman and Alessandra, everything good? Audio, video? Okay, Alessandra, good. Anvithuman, good.
So until now, we have looked at data collection of linked user identities, investigated the biases, and try to solve the problem at the level of proposing a better method to link user identities. Now we shift gears and we look at the control aspect of linkability, which is the user-centric approach. The idea here is, can we help users control linkability of their identities across social networks? So if you recall in the motivation examples, a lot of examples were from the point of view of either social network providers or they were from a third-party point of view. But what about the user? So user may say that my identity is getting linked, so there is a privacy breach. So how do we support the user? So to support the user, we design and implement a linkability nudge, which is essentially a gentle intervention to help user toward making and more informed decisions. So this linkability nudge is proposed in two parts. The first part is the web portal. In the web portal, the idea is that the user decides a range of linkability threshold. So there could be a user identity pair on two social networks. For example, you may want to have LinkedIn, Facebook as low linkability, and maybe Facebook and Instagram with high linkability. So you can configure, as a user, you can configure different ranges of linkability that you desire on any two social network pair. And you can also say, so the second part of the nudge says that the moment user behavior goes beyond that pre-configured range that the user has configured, then a nudge is thrown to the user. So here is the idea. So the users logs into our platform, provides us with the authorization tokens using which we collect the user data, and then we use the state-of-the-art identity resolution algorithms to compute the features using which and once the score is computed, it is shown to the user. For example, for this particular user on Twitter, Facebook, the score is 0.74. For Facebook, Instagram, the score is 0.25. For Twitter, Instagram, the score is 0.26. And for each of the scores, we also show the attributes. And here in the pie chart, we basically show what is the contribution that each attribute is making towards that score. So the second part, as I said, once the score is shown to the user and the user has also pre-configured the linkability scores, the nudge is thrown to the user. There are two types of nudge. One is content-driven nudge. So content-driven nudge is shown whenever the user is making similar posts. And let's say the user has made a post on Twitter and the user makes the same post on Facebook. And the user has said that I don't want Twitter, Facebook, linkability scores to be very close to each other. So I want low linkability. So this red bar is shown around this text box. And if the posts are different, then a green bar is shown. Then another type of nudge is based on the attribute change. So a user can make change in the attribute. On, let's say, Facebook, this is a Facebook attribute page, and the user has made a change, and the user is alerted with a notification nudge. And the nudge says that your linkability with Twitter has increased. So these nudges have been shown to the user by using the web plugin. So we had created two plugins. One was looking at the Facebook posts, the other was looking at the Facebook profile changes. And the way to evaluate this kind of a system, we performed a small controlled lab experiment with two phases. The first phase was control and the second was the treatment phase. Participants were recruited and were told to perform tasks related to making a post or changing the attribute. And we observed that the nudge made an impact to the users. So control phase was the phase when no nudging was done to the user, and treatment phase was the phase when nudges were shown to the user. And this is just a small snapshot of the user activity. So the user can do these tasks, user can make a post, user can make profile change, user can do linkability score range configuration. And then in the middle of the legend, we have the markers for what the nudge can do. So the nudge can show the green post box, nudge can show the red post box, and nudge can show the notification pop-up. This pipe is the control to treatment phase, and we monitored every participant's activity starting, let's say, there is at the bottom, there is one participant P1, and towards the right side, near the 30th minute, before the 30th minute, there have been plus means the post is made, and then a green box is shown, then the post is made, then another red box is shown. So the idea of this evaluation was to get a sense of how the nudge is impacting the behavior of these users, and are there users who stand to benefit from such kind of a nudge. And it did turn out to be successful. So in the last part of my contribution, so we look at the application part, and here we look at an extraneous problem. So why I say it's an extraneous problem is because it is not directly linked to user identity linkage as such across the two networks. So here the goal is to find out user identities which are similar looking identities within the same network. So if you recall the user identity linkage, one of the prominent ways we could identify user identity linkage was based on the user's redundancies or similarities that the user expressed in their behaviors across social networks. But now we said that, let's say, once we have solved that problem across the social network, can we use the same methods, same ideas to solve a problem within the same network, and clone detection is a challenging one. So, in the interest of time, I will only look at the problem. The problem goes like this. So the user identity, which is similar looking identity. So here we have the Twitter verified Twitter profile of a celebrity, a film star, Amitabh Bachchan in India, and then you have similar looking identities of this person, which we refer as the clone identities. And then there are fan pages. So fan pages, the identities which are mentioning fan are not as problematic as these kind of identities which claim that this is my real Twitter account, Amitabh Bachchan. And what these clone identities do is that they indulge in making advisories, they indulge in sharing URLs, some of them can be malicious. So they try to trap people. The idea is to ride on the celebrities' known figures, and then ride on that, and then make these kind of behaviors. The first is sharing a URL, which could be malicious. The second one is making an advisory, and people may tend to like it, and some may get may believe it to be coming from a very known person, so they may believe that it is true. So this is all about on the application part of my thesis. So at the end, I summarize my contribution. The first being performed comparative analysis of data collection methods. Second was investigated the biases. Third, proposed node embedding framework. Fourth, helped user control linkability of their identities. And fifth, applied the UIL solution to detect clones and flag their behaviors. Limitations and future work. So data collection is becoming very, very challenging, and at the same time, in the context of user identity linkage, there is a need to explore other social media platforms like Goodreads and Strava. We employed a situational testing framework, which is a discrimination study framework to quantify the data set biases, but other fairness algorithm studies also need to be explored. In terms of the node embedding, our solution makes use of only the network information, but we would also want to use content and profile information as well. And in terms of the linkability nudge, we performed a controlled lab experiment. A field trial would be a good direction to go in future. So finally, I would like to express my gratitude to my PhD advisor, PK. He has been very supportive all through my PhD work. I also thank my monitoring committee members, Professor Arun Balaji and Professor Rajiv Rishab. They have been regularly providing me with updates and helping me improve my thesis. I also like to thank my evaluation committee members once again for in reviewing my thesis, for helping me improve my PhD thesis. I thank my co-authors, my peers, members of PCOG, and my family, who has been very supportive. They have always offloaded a lot of tasks off my shoulders so that I can work in my PhD thesis. So with that, I thank you all those who have joined through YouTube and all those who are on Google Meet. Thank you for your patient listening. I'm open to questions.
Thanks. Okay, thanks. Yeah, so any questions from students, faculty, others who are on the call? In the Meet call, there's a YouTube question. I will read that out. But is there any quick questions other than the examiners to start with? And not necessarily quick, any question? No? Okay, let me read out the YouTube question. So I'm curious as to why limit the situational testing to only male and female gender, or does this kind of restriction come with the data collected?
Most of the discrimination studies have focused on gender as an attribute, and very rightly so, because there are many instances in the past where one gender, particularly the females, have been discriminated against, and so that was the reason in the situational testing slide I had put gender as an example of protected attribute, but it can be any attribute for that matter.
Thanks, Rishi, for asking the question. Any other questions? Any other questions? Now for examiners, if you want to ask some questions to Rishab,